Okay. Hello. Good evening, everyone. Can you hear me remotely?
Yes, we can hear you.
Hello, hello.
Hello, can you hear us?
Okay. Perfect. Okay, so let me share. Oh, the screen is already shared. Can start. Okay. So thank you for coming, everyone. My name is Emanuele Parisi. I work in the high performance domain specific architecture group led by Professor Michael Moreto. And the idea of today's meeting is to share with you what is the status of the research that we did in the field of artificial intelligence for chip design here at BSC, and to give a report of what we did in the last more or less 1 year. So starting from September 2000, from the beginning of 2025. I would like to give a preliminary idea of what is supposed to be the, let's say, 10,000 feet overview of what we are doing and what will the goal be in the end, besides what we have currently done so far. And then I will talk about two of the latest work that we had, that is the TuRTLe framework and the NotSoTiny benchmarks. And then a very quick wrap up to give an idea of what instead we are doing right now and how we are, let's say, pursuing the research in artificial intelligence for chip design. So ideally, the very long-term goal of this activity at the end of the day is to try to see if and in which way AI can enhance engineer productivity in chip design tasks, starting basically building up basically on three main pillars. So starting from benchmarkings, let's say always trying to keep our eyes on what the state of the art is, what the most recent models capabilities are, and what are the benchmarks in the state of the art that are the most promising and the most useful to try to understand how LLMs or artificial intelligence in general can help electronic engineers at their work. Of course, benchmarking is just the starting point. The true end goal of this activity will be to some extent, develop AI and RTL tools. So to try to improve AI models when AI models are used for chip design tasks. And at the same time, trying to close the loop. So once we have improved AI models, also try to build on top of AI models better RTL tools that in the end, the engineers that works in the field of chip design, so from RTL code generation to optimization to backend tasks and so on and so forth, can really try to make the most of their time using these kind of tools. And so far, in the last year, more or less, we have been working on two major contributions, which is TuRTLe, that is essentially a unified evaluation for LLM for RTL generations in the field of benchmarking. And then NotSoTiny, which instead is a latest contribution that we had, where we try to propose a benchmark for RTL code generation that supposedly try to improve the state of the art of current benchmarks that people are currently using for evaluating LLMs at code generation tasks. So when we started, sorry, let me get rid of this.
If you go to more,
Okay.
hide the controls.
This one. Okay, thank you. So when we start working on this research field, as I mentioned, the first thing we try to do is to go for benchmarking. And so we had a look at the state of the art to check which models were the most used and which kind of benchmarks were available in the state of the art. And what we realized is that the state of the art is actually full of benchmark for chip design, at least for RTL code generation in particular. But no benchmark available could really satisfy all our needs. So basically, each benchmark tests on its own subset of LLMs. So it's not clear how it's not clear how benchmarks ages. So it's not clear how new models with new features on the AI side impact the usefulness of benchmarks. Every benchmark more or less gets shipped with its own different environment, so its own different containerization strategy, its own different benchmarks, its own different harness, which makes kind of challenging to try to scale up experimentation. So we found that if you want to really take a bunch of LLMs and test it on all possible benchmarks available in the state of the art, that would have been a lot of work in terms of adapting every benchmark to every model and so on and so forth. And also, usually benchmarks are not really flexible when it comes to swapping RTL tools. So most often, especially if you work with RTL code generation or with synthesis and things like that, it may be useful to see what is also the impact of different tools in your evaluation metrics. And we found out this to be kind of difficult because essentially not every benchmark are evaluated on all possible tools or are possible to evaluate on all possible tools. And we wanted to came out with a strategy to kind of surpass this problem. And what basically we try to build is this TuRTLe framework, which works as a unified harness to evaluate LLM for RTL generation tasks, actually to evaluate LLMs in general for chip design tasks, which tries to overcome all the issues that we saw before. So we try to have a single harness, a single point of test in which we could load all the LLMs available or that are interesting as of now, together with all possible tasks available in the state of the art, and have a consistent, repeatable experimentation and results to try to understand what are the weaknesses of these models in chip design tasks, what are the strength points, what are the benchmarks that are the most promising, the benchmarks that are completely saturated, so they are passed, they are solved, and it's no longer useful for evaluation. TuRTLe, basically, it's composed of different steps. What we do is, so of course, we have different repositories for benchmarks and for LLMs. So you can get your benchmark and your LLM that you want to test, or your family of benchmark and LLMs. Once you have collected the benchmark that you are interested in testing, you feed the prompts to the LLMs that provides answer solution to the problem in batch. In this case, I'm representing essentially a kind of RTL coding problem in which the LLM receives some specification and is expected to provide some RTL code that kind of satisfies the input prompt. And then built inside TuRTLe, there is a set of tools, a set of metrics that gets evaluated that basically depends on the problem that the LLM is trying to solve. I will detail all these metrics, but basically here the idea is that we try to mimic what happened in the typical traditional, let's say, code generation pipeline. So once you have some code, you start evaluating, for example, if it is syntactically correct, if it is functionally correct, if it is synthesizable, what is the PTA quality. And you do this in batch for all the sample that the LLM generates, and you, at the end, hopefully will gain a sense of how different model performs on different sample or on different benchmarks. And at the end, yes, we have you can create your own leaderboard, or you can, let's say, try to analyze the result and understanding which models are better at which task, at least depending on the benchmark that you selected. At the moment, we started working mostly on RTL generation tasks. And at the moment, we are in our pool of benchmark 3 different tasks. The first one is line completion. In line completion, basically, the idea is that you have full modules implementation. You pick a random line inside the Verilog or whatever language you want to test, and you erase the target line and all the line below the target line. And essentially, what people is using line completion for is to try to understand whether LLM can reconstruct the correct masked line according to the context, so to the surrounding logic and the surrounding source code of the line that gets masked. Then we have module completion tasks in which you want to test the LLM. People is using module completion to test the LLM, to test the capabilities of LLM to reconstruct logic based on some specification expressed in natural language processes, in natural language. So for example, in this case, you provide the LLM with some kind of specification, the interface that the logic has to be compliant with, and then you see if the LLM is able to reconstruct the implementation of an alpha adder, in this case, starting from the specification. Clearly, these are examples, so there are more complex designs, but it's just to fit it in a single slide. And then the third most, let's say, used benchmark, at least as of today, is specification TuRTLe, which is a benchmark that is somewhat very related to module completion. The difference is that in module completion, you provide your LLM with a specification and the header of your module. Instead, in a specification TuRTLe task, it's only specification. So basically, you provide the module, the LLMs, only with the English specification of what the LLM is supposed to build, and the LLM must prove to be able to build the header, the module header, and the implementation from the specification. When it comes to evaluate the outcome of LLMs, we have a set of tools embedded inside TuRTLe, which we use to evaluate the answers of the LLMs depending on the task. So for line completion, what people do is basically they verify whether the line produced by the LLM is exactly identical to the reference line that got in the original design. We know this is not a perfect metrics because clearly in hardware, most often you can express the same functionality with slightly different lines. And the authors of this benchmark use exact matching. So that is the state of the art. Instead, for module completion and specification TuRTLe, as I mentioned before, we have a pipeline that it's somewhat more similar to what actually hardware engineers use to evaluate the quality of RTL. So basically, we support both Verilator and Icarus that we use to verify that the outcome is syntactically correct. In most benchmarks, the prompts come, so the author of the benchmark also provide test benches to verify the functionality through simulation of the LLM answers. So basically, we run a simulation with Verilator to check if the test bench pass. And whatever sample that pass functionality, we try to elaborate it with Yosis to see if it is synthesizable. And if it is synthesizable, we apply a default script to compute post-synthesis quality, which essentially means that we extract PPA from the design generated by the LLM, and we compare the PPA of the LLM design with the PPA of a golden model, of a golden implementation for the same sample, which again, usually the authors of the different benchmark provide. This is as of today, the set of benchmarks included inside TuRTLe. We have RTL repo, which is a relatively famous benchmark that is used for line completion. And then we have Verigen, Verilog and RTLM, which instead are module completion and specification TuRTL samples. We are working to include more designs. First of all, because as of today, basically we are only evaluating RTL code generation, while there are a lot of tasks in chip design and a lot of benchmarks that will be integrated inside TuRTLe to evaluate the capability of LLMs at different tasks. And also from the number of design here, you can see that this is another problem of the current state of the art of this kind of experimentation, because at the end of the day, we only have 200 samples. So you see that all the benchmarks separately, except for RTL repo, are relatively small. And this is another motivation for a tool like TuRTLe. So something that could be useful to concentrate in a single place the largest possible of design possible to make sure that we have, in the end, a number of modules that is in the order of 1,000 or tens of thousands to have a more solid statistical evaluation of the performance of LLMs. This is again a representation of the evaluation steps that we run, at least for module completion and specification TuRTL. Again, whatever the LLM produces, we check if it is syntactically correct, functionally correct, synthesizable, and then we assess the PPA score with a couple of words of caution. First of all, as I mentioned, in TuRTLe for functionality, we support test bench-based functionality. So of course, whatever results and whatever assessment we see in TuRTLe, we are trusting that the test bench provided by the benchmarks author are trustworthy. And the same goes for post-synthesis quality. So when we compare how good, let's say, the capability of the LLM to produce good PPAs in certain tasks, we are comparing with something with a implementation provided by the user over which we don't have real control. So if the implementation is very naive, it's very simple. It may be possible to, let's say, overestimate the capabilities of LLMs. And on the other hand, if you compare LLMs over reference that are very, very optimized by super expert human engineers, it may be easy to actually underestimate the capabilities of LLMs. These are the preliminary, not the preliminary, these are the performance that we could measure in module completion and specification TuRTLe. Here, basically, you see on the y-axis, is a kind of accuracy. So basically, is a score, is a percentage score that tells you how good the LLM is behaving at the different stages of RTL code generation that we evaluated. And on the x-axis, you have syntax functionality. You have the different goals that we specified before. So basically, we measure the capability of the LLM to produce syntactically correct code, functional, synthesizable, and good PPA quality. And there are a couple of takeaways that can be drawn from this preliminary analysis. So first of all, most of LLMs basically tends to generate syntactically correct code. If you get large models, for example, DeepSeek, so models in the order of hundreds of billion parameters, you almost reach 100%, which means that except for a few corner cases, the code generated by the LLM is essentially correct. There is another interesting aspect that you see that there are a couple of models that here do not show up very well, which are the last two, Haven and Origin, which are the red and purple square here. That you see that they perform incredibly well. They basically perform on the almost on the level of DeepSeek. And these are, differently than DeepSeek, these are models that are tiny. They are in the order of 8 billion parameters. And the trick here is that they got fine-tuned on Verilog and System Verilog. Which is to some extent a good news in the sense that it means that if you take a model and you fine tune, you can get performance, at least for syntax, on par with DeepSeek. So with hundreds of billion models using something very small, very local that in principle could run on your workstation or on your laptop. The second major takeaway is that DeepSeek R1 at the moment is the best performing model. As you can see from the list of models that we tested, I mean, from the subset of models that we tested, we are only experimenting for now with open source models, even if TuRTLe is completely generic. So in theory, you could provide to TuRTLe an API key and an endpoint, and you could use TuRTLe to basically to test it using Claude, using ChatGPT, using paid model, essentially. And the other takeaway from TuRTLe is that if you stick to current to current specification TuRTL and module completion benchmarks, the kind of performance plot that you get is that after functionality, the plot is flat. So what you get is that you have high performance at syntax time. Then you have the biggest drop in functionality, which means that a substantial fraction of the samples that are syntactically correct actually are not functionally correct. They don't pass the test bench. And then you see that the line remains flat when you move from functionality to synthesizability and post-synthesis quality, which means that at least for the benchmarks that we have tried, whatever code that is functionally correct, it's basically also synthesizable. So the models do not have any trouble in generating synthesizable codes because you see that we don't lose any sample when we move from functionality and synthesizability. And the same is true from post-synthesis quality, which in this case, it means that whatever code generated by the LLM that is synthesizable, if you synthesize it and you compare the PPA that you get with the human reference, you get essentially the very same performance or the same, more or less the same PPA numbers between the LLM generated code and the human reference. So, which is also an indicator of the fact that most of this sample may be too easy because you are not really stressing the capability of the LLM to either produce particularly smart design or either test the LLM generation on challenging logic where you could see different PPA behavior between the code generated by the LLM and the code of a human engineer. So basically, this is for what concerns TuRTLe framework. So basically, with TuRTLe, we have a unified harness, so some kind of asset that we can use to upload new models, upload new tasks, and really get a unified evaluation, a unified and consistent evaluation of different LLM on different tasks. After we were done with TuRTLe, we realized that what we had, at least in terms of ability of testing LLM on code generation, what we had was really not sufficient in the sense that, first of all, many of the benchmarks that I showed are small in scale. So we're talking about a few or hundreds of samples, 200 samples, essentially, while ideally you would like to test on thousands or tens of thousands of samples to have a robust statistical estimation of the capabilities of LLMs. The second problem is that if you, let's say, open the benchmarks and you see what you are testing LLM on, most of the benchmarks are relatively easy. Most of the prompts ask the LLM to generate simple adder, multiplier, finite state machine, like very kind of simple Verilog or system Verilog exercises in terms of complexity. And then there is a third problem, a little bit subtle problem, which is benchmark contamination, which relates to the fact that most of the benchmarks that we included into TuRTLe are benchmarks that are open source. They are available on GitHub. They can be downloaded and used. And so what we wonder is what happened if now we measure the performance of some LLM on some tasks, then new LLMs came out, and these new LLMs have been either trained or fine-tuned on the very same code, on the very same benchmark code that we are using to evaluate. And this is clearly a problem in benchmarking in LLM evaluation, because it means that when you evaluate an LLM on some code, you don't know if the LLM is generalizing, if the LLM is getting better results because of the new training algorithm that you created, or if the LLM simply got fine-tuned on the very same code that you are asking the LLM to reproduce, and so you're getting benchmark contamination. And to solve this problem, we propose NotSoTiny benchmark, which is basically a collection of RTL code generation benchmarks that are inspired by the Tiny Tapeout initiative. So we use essentially Tiny Tapeout as a fresh, recurrent source of new designs that are novel, that have never been seen in the web and in past benchmarks. Tiny Tapeout basically is an initiative essentially that aims at making the large number of people possible gets their hand dirty with chip design. Basically, in Tiny Tapeout, what you can do is periodically there is shuttles of chips, and what any person can do is buy one or more of these tiles. So basically, you buy a certain area in the shuttle that they create. Every tile it's sold for a couple of €100, I think. And what you do basically is, if you're interested, you pay the tile, you submit your project, your very own custom-made project online, and the project gets downloaded, gets packed together to create the shuttle, and then it gets fabricated, and you receive the PCB after 2-3 months in your place. And this is really Tiny Tapeout is really the fuel that is fueling the NotSoTiny benchmark, in the sense that in order to fight contamination, we need a periodically regenerated, fresh source of new design. And that's exactly what Tiny Tapeout is. Every approximately 3-4 months, 6 months, Tiny Tapeout releases a new shuttle, which means that potentially new people will upload their new design online that we will get to have a code base of fresh design periodically. Now, the problem is, once we have identified the source of code, which is Tiny Tapeout, we have to understand how to build the benchmark. So how do we prompt the LLM? What kind of tasks we can create out of this Tiny Tapeout? And what we decided is to go for module completion. So what we do basically is for every project that we fetch online, we have a set of modules essentially, which constitute the project that the user submit for fabrication. And for every module inside each project, we build samples by selecting one module in the project, by masking the module implementation. So for example, in this case, the user wants to fabricate a report carry adder. There is the top level entity, there is the full adder. We are masking one of the module, and we are asking the LLM to reconstruct the logic of the masked portion of Verilog or system Verilog according to the module interface, which we don't touch, and according to the surrounding logic. So in this case, the LLM is supposed to understand that there is some kind of object that is called report carry adder. The report carry adder is calling some module, full adder. Full adder exists, but it is masked, and so the LLM is supposed to understand what he has to do. So to understand the implementation of a full adder, providing the full implementation by using the context as surrounding logic. This is one sample. The second sample is exactly identical to the first one. So we ask the LLM to do the opposite things. We provide the full adder. We tell the LLM that there is a module called report carry adder that has to do something, potentially using this module, and then we see if the LLM understands that according to the context, it has to instantiate, in this case, the chain of full adders. This is a representation of let's say, a more complete representation of the pipeline that we use to start from tiny tape out shuttle and to get our benchmarks. Essentially, at the moment, there are more or less 10 tiny tape out shuttle, maybe something more. We download shuttle from tiny tape out shuttle from number 6 to number 10, simply because the early shuttle have a format that is a little bit more challenging to handle, so we discarded it. We discovered projects basically that are not Verilog projects. In tiny tape out, there are people that submit projects in Verilog, but also in VHDL, in Chisel. They submit analog designs for fabrication. And clearly, at the moment, we are only interested in Verilog. For convenience, we take all the source codes of the project, and we merge all the source code using Verilator into a single file. Then we build the task according to the module completion logic. So what I described before, basically by masking one at a time the different module present in every project. So if you have a project with n modules, basically you get n different samples for your benchmark. And finally, we take all the samples that we have so far, and we run temporal deduplication routines. This is just because we noticed that since Tiny Tape Out is an initiative mostly directed at hobbyists and people passionate about chip design, it's very common that the same person submit the same project multiple times, or that different people tends to submit the same project. So to avoid having task duplication, we basically run a simple deduplication step to make sure that every sample that we have in the benchmark is kind of unique. And with this pipeline, we basically enhance by one order of magnitude the number of samples that we have, because we pass from 200 samples, which is basically the aggregated number of samples that we had by collecting samples in the state of the art. And in this way, we reach in the order of 2,000 samples. So we gain one order of magnitude of evaluation capabilities for the NotSoTiny benchmark. Once we have a policy to build the samples, to build the benchmark, we try to understand how we could verify the output of the LLM. And here it's where things get a little bit trickier, in the sense that what we did is we tried to evaluate how good test benches are in the NotSoTiny benchmarks. And we realized that we created this plot, which basically is a scatter plot where every dot, every bubble is a project, so it's test bench, essentially. And on the X and Y axis, you have the number of assertions that the test bench executes. And the coverage, here coverage is the code coverage automatically extracted from VCS. And what we realized is that if we realized on the user-provided benchmark to perform functionality evaluation of the samples. This could lead could lead to a poor experimentation, because you see that more or less 50% of the benchmarks have a code coverage that is slightly higher than 60%. And the most concerning things is that if you count the number of assertions that gets executed by every benchmark, you see that there is approximately 50% of the samples, not so tiny, that do not have assertions. So the benchmark is not self-testing, which means that if you have a code that is syntactically correct, you run the benchmark, but the benchmark will always tell you that the benchmark passed. And so for 50% of the sample, you don't have any way to verify whether the design is correct or not. And this match the feature of the Tiny Tapeout initiative of being mostly directed to hobbyists and not requiring people that submit design to have a really solid verification pipeline. What we did to overcome this problem is we relied on formal verification. So essentially, we cannot trust the test benches submitted by the user, but we have the golden design, because we have the design that the user actually submit for fabrication, which is the real, let's say, golden logic that LLM should, in theory, reproduce. So what we do essentially is, whenever an LLM produces a design, is we load the original user design that we call golden for facility. Then we load whatever the LLM produces, which we call gate. The designs have the same interface, because we build on purpose the benchmark, the problem, so that the LLM is never requested to change the interface between modules. And what we did essentially is we built a meter circuit. So essentially, we short the input of the two modules, and we put an equality check at the output of every pin in the output assignment of the module. And we try to verify whether the trigger pin is always 0 using a satisfiability tool. So trigger is something that is a single bit pin output that, in theory, if the design is perfect, should always be 0. So because when trigger is 1, it means that basically there is a difference at the output pins, at least one of the output pins of the two modules. We want trigger to be always 0. If trigger is always 0, it means that there is never any mismatch at the output for the same input. And we proved it with a satisfiability tool using temporal induction. And since formal verification can take very long, we basically stop the experimentation. We allow the tool to make at maximum 30 steps, which means that if the tool cannot find any mismatch within 30 steps or within the 15 minutes timeout that we provide, we essentially assume that the generation is correct. And the rationale behind this is that we did a couple of experiments with this, and we realized that this, at least for this kind of designs that are more complex than the average benchmark that you find online, but are not also terribly complex design, usually the satisfiability tool, if the design is buggy, the satisfiability tool is able to find a mismatch basically in milliseconds or in seconds. So if after 15 minutes the tool cannot prove equality, but also cannot find any counterexample, we assume the generation is correct. These are some results from the NotSoTiny benchmark. The best model in this case, it happens to be not DeepSeeker 1, but to be this other open source model, which is called Point3Coder A35B. It's interesting because it's not the biggest model. So in TuRTLe, we observed that the biggest model, so the models that have more weight, tends to also perform better in general, while here we observed that a model with more or less half of the number of parameters with respect to the top model still performed best. We confirm what we saw in TuRTLe, that basically syntax tend to have a very high score. Here we have almost 90% of accuracy on syntax, which means that at least these classes of model are very good at syntax. Whatever value they will give you tends to be correct. But we observe a very sharp decrease at functionality evaluation evaluated with equivalence checking. We see that The best models basically can barely surpass 21% of accuracy, with the top model being less than 25%, 23.4. And we observe what I just mentioned, that equivalence checking, so functional verification carried out with equivalence checking, brings down accuracies a lot with respect to test benches. And in fact, from this plot, you can see the three bars, blue, orange, and yellow, where orange and yellow are the accuracy or NotSoTiny benchmark when you evaluate the test benches in orange and the yellow, in equivalence checking in yellow, to assess functionality. And what this plot is telling you is that if you run NotSoTiny, neglecting functional verification, neglecting equivalence checking, so if you basically neglect the yellow bar, NotSoTiny is a useless benchmark, because you see that you don't have any accuracy drop between functionality evaluated with test benches and syntax, which means that you give a problem to the LLM will give you something back. If that something is syntactically correct, it will also automatically be functionally correct, which is a nonsense, essentially. And it's something that we also don't observe in CVDP and in RTLM, that are other module completion specification to RTL samples. Which also means, to some extent, that formal techniques are, let's say, are very picky at evaluating designs, but they are a promising way for basically assessing the capability of LLMs in settings in which you cannot, either you don't have a test bench, or you cannot trust, or you don't want to trust the test bench created by the user. This is the work that we did in the past year. As you see, there is a lot to do, in the sense that the space of chip design is basically infinite in terms of tasks. We mostly focus, actually, we only focused so far at the HTL tasks, so RTL code generation tasks. And within RTL code generation, at the moment, we only focused on Verilog and System Verilog. And also in terms of tasks, as you can see, basically we only tackle benchmarking. So we mostly focus on assessing what the real actual capabilities of current open source models are at this kind of tasks. But we have many, at least 4 ongoing activities at the moment that we are pursuing. So essentially, still at the HTL level, we are carrying on an activity that is what we call grammar-oriented module completion. Basically, it's an extension of NotSoTiny, in which instead of asking the LLM to generate the full module implementation, which for real design is too much, you get 0% accuracy. We try to find a way to strip the logic that the LLM has to produce. So out of a module, we try to ask the LLM to produce, for example, only a subset of the logic of the module. And we use the grammar of the System Verilog language to formally select which kind of logic the LLM has to implement. In the verification team, there are people working on SVA generation from Golden RTL, which also is a very interesting task. And there is, in the state of the art, a lot of attention to how to use LLMs for verification, especially for formal verification, for System Verilog assertions. So it's a very interesting task that we are pursuing. For what concerns synthesis, we are trying to enhance the pool of benchmarks that we have in TuRTLe, to integrate a couple of benchmarks that got recently released that try to investigate whether, let's say, how good LLMs are at providing PPA optimized code. So what these benchmarks do is prompting the LLM with a module implementation in Verilog, and they ask the LLM to produce an optimized implementation, an area optimized implementation, or a power optimized, or a delay optimized, and so on and so forth, and evaluate the capability of the LLM to do this without feedback, or with synthesizer logs feedbacks, and so on and so forth. And then we have people, actually we have one person that is starting the master thesis working on chip planning with diffusion models, which is also a very interesting and a very innovative approach to chip planning. In the state of the art, most of tools to do automatic floor planning or automatic chip planning, they work they are either fully analytical model. So they are a model that create a mathematical formulation of the problem, and then they use convex and not convex optimizer to basically to try to come out with a valid floor plan. Or in the state of the art, for what concern learning-based models, there is a lot of reinforcement learning. So a lot of people that tries to basically train different kind of reinforcement learning to place macros, place partition of the circuit to create a floor plan. And this idea of using diffusion model is something very new that comes out of Berkeley, I think. And there is a student that is investigating this possibility. These are the references to the two paper. I covered only a subset of the material, but if you're interested, these are two papers accepted at MLCAD and submitted at DAC. And I think that's all. So if any of you have questions, I will be happy to answer. Yes, I will see.
Thank you very much for the presentation. And I can feel your pain for lack of, let's say, reliable artists
Yeah.
for doing this. And yeah, probably it's one of the most complicated part, right? And to find them. I have a question about the slide 21.
Yes.
Or maybe 11. Yeah, 21 also.
Yep.
So maybe first, maybe can I ask you, do you believe that this trend that you observed from stage of functional benchmarking to stage of the last stage of benchmarking is something what is assumed to remain overall when you you continue improving benchmarking, or you anticipate that this trend will change? Is it something like what LLMs truly put, or maybe it's lack of benchmarking metrics?
No, I believe it's a matter of benchmarking metrics. So what I think it will stick is this line from functional to synthesizability. We didn't see. So let's say when LLM generates code, we didn't see any weird kind of generation that may trick the LLM into generate code that is not synthesizable. So I am fairly confident that that will let's say I don't think that synthesizability will ever be a terrible problem to tackle. Maybe we will wrong. But instead, for post-synthesis quality, so for PPA evaluation and actually, let's say, actually investigating whether LLM can produce code that is really on par with what a well-trained engineer can do. For sure, there is still a lot to do in terms of benchmarks, because most of the so at the moment, post-synthesis quality is evaluated only in these three benchmarks: Verigen, Verilogval, and RTLM. And in all of these three benchmarks, you are asking the LLM to generate very, very simple code. So we are talking about report carry adders, we are talking about multipliers, and we're talking about like simple, semaphore, finished state machine, something that is more or less on par. Not for all, but most of sample are like that. Something that is on par with Verilog exercises. And so the problem that we are at the moment experiencing with post-synthesis quality is that, first of all, we don't have, at least here in this benchmark, code generations, so prompts that describe systems that are sufficiently complex so that the LLM can really either show particularly smart implementation or show instead particularly problematic implementation first. And the second point of post-synthesis quality that at the moment is problematic for how we evaluate it right now is that, first of all, at the moment we are using only open source code, open source tools. So what we do is we load the design in Giosis, and inside Giosis, so we're using OpenLane. Inside Giosis, there must be a default ABC script that gets used for logic synthesis. And we are assuming that that script is significant, let's say it's representative of all the optimization that you can do. And we're not using also commercial tools. We're not using Synopsys or Design Compiler and stuff. That will be actually a step also very important because there are papers that shows that the outcome that you see when you evaluate the capability of LLM to produce good PPA code, it's completely tool dependent. So if you synthesize with Yosys plus ABC, you see something. If you synthesize with Design Compiler, you see something completely different. And that's at the moment a problem of benchmarking in this area mostly. But the biggest problem, I think, is the first one that I mentioned, that there are no designs of a complexity sufficient to really try to understand what's going on. So yeah. So the final answer to your question is no. I think this line may ban. This one I don't think so, but this one yes, probably yes.
And one small question additionally just to the last two stages. So there you rely just on the reports of synthesis tool, right? You don't do any additional functional checks on what has been synthesized, right? You don't do any.
No, post synthesis. No. What we do for evaluating synthesizability is again with Yosys. We do, I don't know how many are confident with Yosys, but we do read verilog, then we do hierarchy. And if the hierarchy pass does not fail, which should be kind of the equivalent of elaborate when you design compiler, if the hierarchy command does not fail, we assume it's synthesized. And post synthesis, we have the netlist, but we don't do anything with the netlist. We assume that it's correct. Even if what I mentioned, so I mentioned that I don't think that synthesizability will ban, but there is also another issue here that, of course, again, we are evaluating on simple samples. So I don't know if using more complicated, more real-world designs may kind of trick the LLM to generate code that becomes non-synthesizable, or that, let's say, put in crisis the whatever synthesizer you want to use for PPA evaluation. So the major takeaway here is that, and this is one of the reasons for NotSoTiny, is that everything that you see here and everything that you see in paper in the state of the art is strongly biased by the fact that the design that we are testing on are easy. At least if we talk about these three samples, if we talk about these three benchmarks, Bergen, Berioga, and Dr. Yeah. Thank you. I don't know if there is something in the chat, maybe. There are questions, sorry, in the chat. So there is a question from Manju Nath. I hope I pronounced correctly the question. Is it a nice work, nice presentation? Thank you. Are you working on reasoning part, which will help for approximately correct logical code generation? Not explicitly, in the sense that we are not explicitly using reasoning capabilities for any purpose. What we observe is that reasoning LLM model tend to produce better results. We are not doing anything at the moment with the reasoning trace. So we are not trying to understand whether from the reasoning trace you can get some implementation that is quasi-correct or not 100% completely correct. So this is something that we are not tackling at the moment. Okay, and there is no other questions.
So do you plan on taking with commercial LLM? Like Gemini?
I think we have partial results with commercial LLMs. Do you want to elaborate on this?
Partially, like the commercial LLMs need credits or money.
Yeah.
So the scale is much more crazy. So but we start like closely to add some months, and we have this trend that commercial are more superior to those. So there is this gap also.
And do you have some estimations of the cost? No. perhaps you have talked with a provider or with different.
We have plenty of, we have planned how we can approach this and we still discuss our plan.
So at the moment, TuRTLe supports the usage of let's say commercial models, in the sense that we have support for you putting an API key with an endpoint and prompting whatever is up there, or Gepetto potentially. But we haven't extensively experimented with this.
But there is a leaderboard that you can check, and we are trying to update the problem. So
It's online.
yeah.
But it's oops. So just to cancel. Just to give you an idea, the leaderboard that Razin was talking about is this one. So if you search for TuRTLe Hugging Face, essentially, you get this leaderboard, which is updated with the most up-to-date model. You see that here you will see some models that I didn't present in the results because we added them later. And essentially you can select which kind of model you want. So for example, give me the result only for general model. And you can, for example, ask, give me the result only of specification TuRTLe, evaluated on RTLLM with Verilator. For example, there is a number of parameters that you can set, and this will give you the live results of the benchmark, which in this moment actually is still CCAR1. But this is something that we periodically update, so feel free to check it. And it should be reasonably easy to find. So yeah.
I'm thinking about you, right? I haven't been doing this a lot of talk, but one of the things I keep telling my members of my team is that the first design and implementation is not important. You have to think in terms of maintenance, and for that you have to write your code in a way that somebody else will be able to maintain it, and also you have to document it so that somebody else understands it. Do you think using LLMs is going to change that? There's no need for maintenance anymore, and there's no need for documentation, because the LLM will start from scratch every time.
So I would also like think loudly.
Yes.
So I think there is something that you can observe, which is the fact that LLMs works incredibly better, at least at RTL code generation, I mean, if you provide well-documented, clean, like with meaningful naming, let's say generally speaking, well-documented and well-written code and clean code. I have no doubt of this. So it would be very cool, I think, if we could, let's say, if this could become a positive feedback. So kind of people want to use LLMs, but in order to be used, the LLM have to work. And this becomes, and since LLMs works better on polished, documented, clean source codes, then this becomes a kind of positive force to force people to produce better code, so that not because better code is better than worse code, but just because LLMs will work better and produce better results, at least in terms of functionality, I'm talking, with respect to having a code base that is undocumented, where variables or signals are called with ambiguous name and stuff like that. But I'm not sure if LLM will ever, let's say, I cannot imagine right now if LLM will help in the maintainability of code bases per se. So I don't know, but I'm a bit skeptical maybe, but I'm not sure if you could do a process like, okay, let's start from a very poorly documented design, but functional, but poorly documented design. Let's start using an LLM to improve feature, so to add feature, to design new components, or to improve the functionality, for example, of this design. And by product, the LLM will also kind of improve the quality of the code base and stuff like that. I would be skeptical. I don't know. I think everything works smoother if you feed the LLM. So if you drop your LLM in a code base and in an environment that is already clean, it has already as much as possible clean interfaces. What we observed in a couple of ablation tests that we did is that having clean interface, for example, is crucial. If you have, for example, an interface with data valid ready, it's kind of weird, but unless the model is very simple, if you have the very same logic but valid and ready, instead of calling valid and ready, you call it okay and go on, exactly. You will have somewhat worse result to some extent with respect to this to polished code base. But this is kind of speculation. We didn't really investigate.
So I understand that based also on the work that you have done, but you could also provide some kind of feedback to the designers, right? To prioritize some best practices and the way they write code, just for helping you also perhaps to train this or not.
This is something that we didn't systematically experiment with. This is just mostly what I said is mostly because of I partially try to use these tools and for very simple stuff and that's basically what I realized. If you let's say in order to make the most of these tools, you have to make the tools in the condition of to work in the best possible condition. So every time that I started a task based on LLM, I asked the LLM to modify something in Sargentano or something, assuming that the LLM is super smart, that whatever any other detail will be useless because it can already work by itself. It always ended horribly. So, but never say no.
And how the work that we have a lot of engineers here and researchers working on design accelerators, writing code, how these work could help you also on making these more robust.
So one of the things that we are trying to do is trying to in the limit of, so if it is possible, so if we are not talking about sensitive IPs in terms of disclosure, we are trying to increase the complexity of tasks by simply picking larger designs. So what we are doing, for example, there is something I didn't mention. We are also starting with our student in our group with, say, some tasks related to agentic code generation. So a situation in which you don't simply prompt the LLM to do something, but you also give the LLM access to tools, so to synthesizers, to simulators, to logs, and stuff like that. And for that task, what would really benefit, I think, is even scaling up the design just to the level of Sargentano. So nothing crazy complicated, but even just that will really improve, I think, the metrics, the analysis of result that we can get. So in general, if you can suggest code that we can use, that will be very useful. What we are seeing here with chip learning, there is a collaboration between us, people in the physical design group, and professors from UPC. Having access to domain expertise, it's super important, even just to set up the problem. Sometimes one of the problems of the papers in the state of the art is that sometimes problems are not set up in the correct way. So you are asking the LLM to do things that an electronic engineer will not necessarily ask the LLM to do. So also having access to domain expertise, and then having access to people willing to work on this. So we have many ideas, but if any one of you have ideas in terms of new tasks that we could tackle, better data, or suggestion in terms of the pipeline that we set up, this is more than welcome.
I think we have to be very careful. Yeah. We, for contractual reasons, there's quite a lot of stuff that we do that is not public. Is not, and we are forbidden from making public. I'm not sure what we mean to train and everyone or anyone using things that have been related. For example, we have academic or research licenses, and you might not think so, but you cannot open source anything developed with that kind of license. You have to have a commercial license in order to open source.
Okay,
So
that's
that's a problem. We are trying with the BSC LOCA to put a lot of stuff in open source, right? And that's the one that's fair game. But I'm thinking of the backend nodes. We have to be very careful with anything we do. And I understand the tension between doing research and trying to improve your tools and then respecting any kind of commitment to that.
So to some extent, we are trying to tackle this, first of all, by, at the moment, everything that I showed is built on fully open source design, decays, and everything. So that's let's say, we know that we are restricting the quality of the analysis that we are doing, but we did that exactly for the reason that you mentioned. So to avoid troubles, we synthesize with ABC, in Skywater 1/3, so that we can release whatever we want, we can fine tune on whatever we want, and the same goes for RTL code. So the reason why we are trying to tackle Sargentana, for example, it's because, first of all, it's already open source, so there is not much that we can risk to, let's say, there is no risk of disclosing something that cannot be disclosed, first. And second, I think that at least at the moment, we have some margin to produce some improvement in terms of these tool chains and these tools, using tools like using design like Sargentana, and I think we have more space between we reach the point to which also Sargentana is too easy, and Sargentana, but to say CVSX, to say CVFPU, this kind of system, I mean, to reach the point in which these systems are also too easy, so we really need to go for something really bigger. So that's a way that this does not solve the problem, but that's a way to gain some time, essentially. And hopefully the academic, like the community of researchers and people around the world working on, in this case, system value, but in all the languages, will hopefully come out with more and more complex design so that we can, as much as possible, avoid being in a situation in which everything that is commercial free, so everything that is Creative Commons, let me say, is completely saturated, and we cannot advance the state of these tools without getting into licenses, into intellectual properties and stuff like that.
Emanuele, have you taken a look to the survey, the serial risk by points is modest, risk by points open source is documented, and it's vast most implemented. So perhaps it could also help you to do some experiments with that. It's
It's the most complex thing we have in local. No, I'm not.
Yeah.
We have been thinking what to do with LOCA. LOCA is a step more complex than Sargentana. It's a mixture because it has an out-of-order execution pipeline, whereas an in-order memory pipeline. We would like to make it open source, but we don't think it has the quality and the sharpness that we would like, before we would. I wonder if this can help make it better.
Yeah.
I mean, we need to discuss this, but it might be a challenge if we can improve.
Yeah.
Also thinking, I guess, in terms of systems, in the sense that now, I mean, I mentioned Sargentana because it's the one that I know better, but maybe working on more on a system level without going into the core. I know that Saudi, I think, should be open source. Should be available now. So there is that one, for example.
It's in GitHub, so it's.
Yeah. So yeah, there are choices out there.
E-processor initially was planned to be open source. I don't know
Okay.
what e-processor.
Okay, but
But I don't think they open source. Yeah. So open source is a big cost, but then it's empty most of the time.
it's also a matter, to some extent, it's also a matter of language, because, for example, now everything that I said, everything that we did so far is constrained to system variable because we know system variable, and here we use system variable. But for example, if you scale up to chisel, probably, I know that there are a couple of,
That scale up.
sorry,
How is going to chisel scale up?
because I know there are bigger, sorry. Okay, so if there are no other questions, I think we can close it here. Let me see if there are questions here by any chance. No, I think no. Okay, then thank you everyone.
Thank you.